and welcome class to part 4 in our chapter 14, where again we are still talking about reaction kinetics, reaction rates. The last variable that we really have to introduce when it comes to understanding reaction rates is the variable of time. Since according to collision theory, our rate is going to be equal to the number of effective collisions divided by time, it seems like the reaction rate's relationship with time is fairly straightforward, since as time increases, our rate would potentially decrease, according to this simple equation. However, there's something else that we need to consider, which is that as time passes, as time increases, we also have a greater chance of a number, for a number of effective collisions, right? As time passes, the number of collisions is also increasing. So chapter 14, part 4 here is going to be all focused on how time is going to allow a greater number of effective collisions, which at the end of the day is going to give us a slightly more complicated relationship with our reaction rate compared to the previous variables that we've talked about. All right, so again, our reaction rate is going to be dependent on time. And as time progresses, the number of effective collisions is going to increase, but our rate will still decrease as time progresses. Now we can explain this visually using the GIF that's, moving on our slide right now. At the start of a reaction, we have, let's say, potentially two different reactants, and as these things collide, we can see here that the little circles change colors. They all start either light blue or dark blue, and as this reaction moves forward, we end up with more black circles and red circles representing the creation of products. But we can see that there's this really rapid start of the creation of this black product, and the red product kind of pops up. But over time, it seems like the reaction kind of stops progressing. It stops creating new product. And the reason why is there is fewer reactants left. Since there's fewer reactants left, it's going to take more time for these reactants, which might end up being on totally opposite sides of this container, to find each other and generate any additional product. This also helps to explain why in graphs like we saw in part 2's lecture, why these slopes here are not straight lines. In other words, we do not have a straight and steady relationship between concentration and time. We have this curved relationship, where at the start of the reaction, we have a steeper slope, signifying a greater reaction rate. And as the reaction progresses, we can see that this curve gets flatter and flatter, signifying that the reaction rate itself is slowing down. So what we're going to be looking at here today is, despite this changing variable, how can we find the reaction rate explicitly dependent on the variable of time? How can we measure time and give a prediction for what the reaction rate, as well as what the concentrations of our reactants and products will be at a specific time point along this x-axis? All right, so we need to talk about how to solve for this time dependence. I could just straight up give you the equations that you need, but you're not going to have any context for where they come from, and there are a number of equations that will depend on explicitly what reaction you're working with and what the rate order of your reaction is. So what we're going to do is just work through one of the derivations to solve for the time dependence explicitly, so you can see the rationale of where these equations are going to be coming from. All right, so the progression of our reaction depends not only on the time point specifically, but as we have seen, on the change in time. This is going to be incredibly important for us as we move forward solving for the time dependence. All right, so let's say hypothetically, the following reaction of the decomposition of ozone into O2 gas as well as just single oxygen gas is found to be first order. Now, this tells us that the decomposition of ozone is, or the rather concentration of ozone as it decomposes, is directly proportional to the rate. Now, this we have seen already. We can see here rate is equal to our rate law expression. K is equal, or K times the concentration of O3 raised to the 1. This tells us that as the concentration of our reactant increases, our rate is going to increase proportionally, right? So if we double the initial concentration of our ozone, we would see a doubling of the rate. If we triple the concentration of our ozone, we would see a tripling of the rate, etc. Now we're also going to assume, since we're working with the same consistent equation, our activation energy is going to be constant. And similarly, since we're trying here to observe the time dependence of our reaction, we're going to keep our temperature constant as well, meaning that our rate constant K is in fact also going to be a constant. So we don't need to worry about the rate constant K impacting our rate or causing any fluctuations here. Now, early in part 2's lecture, when we were observing the concentration dependence of our rate, we also learned that if we're paying attention to our reactant, we're going to be observing a rate of consumption, where the rate, as is dependent on that one reactant, is going to be equal to the negative change in the concentration of O3 divided by a change in time. Now here we can see we are explicitly incorporating time into the calculation of our rate. This equation, the rate of consumption equation, is where we would be useful when observing this type of graph we can see on the right, where we're measuring concentration over time. And again, we can see that this is a curved line. There is a power relationship here. It's not a linear relationship. This reaction is first order. And so what our goal is going to be is to rearrange our equation that has the rate of consumption to remove the change in time variable to give us simply a time variable. In other words, our goal here is to be able to create one single equation that is going to allow us to plug in any time anywhere on this x-axis and be able to determine what our concentration is. Now, because our curve here is not linear, it's not going to be as simple as just like finding a straight up y is equal to mx plus b. That is our goal, is to create a really nice straightforward relationship, but it's going to involve some complicated math in order to rearrange what I have just boxed to give us one single t variable as a function or in relationship to concentration and our rate constant. Again, as we move forward, and I'm going to give myself this blank slide here, this space to work, what we're going to be doing is taking our rate of consumption, this negative change in the concentration of O3 divided by change in time, setting it equal to our rate law expression, since this is going to incorporate all of our temperature dependence, our activation energy, giving us some like significant value, like relating to the explicit equation we're working with, multiplying this by the concentration of O3, and this is again first order, so there should be an exponent of 1 here. Just for clarity's sake, I'm going to drop that 1 because anything raised to the exponent of 1 is just itself. All right, so what I want to do here is, again, solve for t. We want to get that delta out of the equation so that way we have a relationship here between just a straight up concentration measurement, a straight up rate constant, and a straight up time. So the way that we're going to do this is rearrange all of our concentration values on one side of the equation and pull our time to the other side of the equation. So first, I'm going to take this delta t and multiply it up to the right-hand side. I'm also going to take this concentration of O3 and divide it down to the left-hand side. So this gives me a negative delta concentration of O3 divided by concentration of O3. And we can't just cancel these things out, again, because this delta is here. This delta represents a change in the concentration of O3. Now this is going to be equal to K times the delta of t, right? K times the change in time. Now, what is this delta? What is this change if not a representation of the increments of which this variable is changing? In other words, I'm going to drop this delta and change this equation into a notation that might look a little bit more familiar for those who are, let's say, comfortable with calculus. Negative d concentration O3 divided by concentration O3 is equal to k times dt. Now, if you're not comfortable with calculus, that's perfectly fine. I'm never going to be asking you to perform any type of derivative or integral in this class, but I do need to demonstrate, again, where these equations that we're going to be using and seeing in a couple of minutes are coming from. Otherwise, without the context, I can promise they are going to be just as confusing as heck. All right, so again, what we're doing here is removing these d's to give us something, an equation that just has straight up concentration and straight up t. So what this means is that we're going to have to take the integral of both sides of this equation in order to remove that change in variable. All right, the range with which we are going to perform this integral on the left-hand side is going to be going from our initial concentration, because that's the maximum on one side for our equation, and then we are going to take this integral all the way over to whatever our concentration could be. It doesn't necessarily have to go to 0, which we'll be talking about more later. So we're going to leave this as just generic variable concentration of O3. Now our time is going to start at the most extreme on one end, a time equal to 0. But again, a reaction could potentially go for like hundreds of thousands of years, all depending on the reaction. So we're not going to put any specific number here, limiting what our integral could be. We're just going to leave variable t here. All right, so I'm going to continue my work up on this right-hand side. In order to take this integral, what we have to recognize is that on the left-hand side, we have variable 1 over x. And on the right-hand side, we don't even have an x, right? We just have constant k. This actually creates a fairly simple solution for our integral. The left-hand side of our equation will end up being equal to negative, since there is still this negative sign here, parenthesis, natural log of our final condition, the concentration of O3, subtracted by the natural log of the initial concentration, our starting point for the integral down here. This is all going to be equal to k times our final time t minus our initial time 0. And so if you, again, are like rusty on your integrals, or if you're not comfortable with integrals, that's fine. But I do want to demonstrate for those who are, let's say, a little bit more comfortable, again, where these equations are coming from. And even if you don't get calculus, at least you can see that there's a rationale for how these equations are being derived, right? We're not just like pulling these things out of thin air. All right, so all we have left to do now is to rearrange and give us an equation, let's say that's going to make sense graphically speaking, something that is going to have us, or have a really nice, consistent, independent variable in relation to a dependent variable. So what we're gonna do is take our negative sign and distribute it to each of these things inside of the parentheses. So we're going to have a negative natural log concentration of O3 plus natural log of initial concentration O3, where this little not symbol, I realize I haven't addressed the subscript. This subscript stands for initial conditions. So the textbook has been, or I'm sure at this point has been using it. If you've been reading along, you've seen this definition already, but it's really useful for us now that we have both a concentration of O3 at some time point t versus this initial concentration to really signify which is which. And that's what this little subscript of the not means. Now this is going to be equal on the right-hand side to k if we distribute this k to both pieces inside of the parentheses here as well. Or times k t, sorry. We're distributing the k to the t as well as to the 0. All right, so what's gonna make the most sense in terms of independent variable versus dependent variable? Now that we have just kind of like this one nice sort of equation, we're looking here to rearrange to give us something that makes more sense. Well, we want the y value, what we keep on the left-hand side, to be our dependent variable, the thing that we're measuring. Well, it makes the most sense for the thing that we are measuring, in this case, to be concentration. Since we have some type of initial concentration and we're looking at how this concentration changes over time, our concentration at some time point in the future is going to be our dependent variable. And our t, our time, is the only other variable here that remains. Since the initial concentration is like a set point, a condition that is determined once you start this reaction, and of course our rate constant K is also constant. So our time here is going to be the independent variable. So now we're just going to move everything to the right-hand side that is not the dependent variable. So this means we're going to keep the negative sign here for the moment. Negative natural log of the concentration of O3 is going to be equal to KT minus the natural log of our initial concentration. And of course, again, if we're trying to rearrange and solve for this O3, we're going to take the negative sign and move it to the right-hand side of the equation, giving us the natural log of O3 is equal to negative KT plus the natural log of O3. Now we're going to leave the equation in this form now because we can see initial concentration, realize I dropped that not, sorry. Now we can see that we have a y is equal to mx plus b. So we have taken an equation at the start here that represented the relationship between concentration and time in a non-linear way. Again, to go backwards, concentration versus time here we can see is a curved line. But by setting these two rates that we know are going to be corresponding to the same rate, right? The rate of consumption equal to our rate expression, both of which corresponding to the rate as determined by O3 in this reaction. We've set these things equal to each other and used calculus, like through taking an integral, to find now a linear relationship between concentration and time. Now this equation, to move forward in our lecture, is known as the first order integrated rate law. Rate law, coming from our rate law expression portion of the equation, integrated because we took an integral to find this equation, to find this linear relationship between concentration and time, and first order because this equation only works for first order reactions. In other words, if the decomposition of your reactant is first order as a function of time, if you have this type of a curve, by taking your concentrations and inserting them into this natural log of concentration of X, where X is your reactant here, here, and setting this equal to the negative rate constant times t plus the natural log of your initial conditions, you will find a straight line. In other words, if you take the natural log of your measured concentrations as the reaction progresses, if you take the natural log of the data points on your y-axis as a function of time, if your reaction is first order, you will see a linear relationship in the concentration versus time data. Now this relationship is super useful for giving us another way to find our rate constant K, since the slope of this equation, again, we're taking a y is equal to mx plus b format, the slope of this equation is equal to negative K. And so the slope of this line can be useful for finding our rate constant. Similarly, our y-intercept, our b here, is equal to the natural log of the initial concentration of our reactant. So in the previous example, the thing we just worked through, x would be equal to O3, because that was the reaction literally we were working with, but this could be any one of our reactants if the reaction itself is first order in that reactant. So the takeaway message here is we have now found an equation, that relates concentration versus time in a linear and expected way. This is super powerful because what it means for us is that if we know the initial concentration of our reactant, and if we know the rate constant for the reactant, we can determine the concentration of that reactant at any time point in the future. It doesn't matter if it's a second from now or a million years from now, we'll know what the concentration of X is at any point in the future. Provided also that your reaction again is first order. So what we're going to do is work through an example problem seeing how useful the integrated rate law equation can be, and then we're going to turn our attention to the other integrated rate laws corresponding to reactions that may not be first order. We're not going to work through the integrations to find the other equations, but know in the back of your head that each of the equations that we will be talking about were derived in the exact same way as what we found the first order integrated rate law. We're going to have to set our rate of consumption equal to the rate law expression, work through an integral to derive a linear relationship between concentration and time. All right, but before we get ahead of ourselves again, let's actually look at using the first order integrated rate law. Let's look at the power of having this equation that relates concentration and time. So let's assume that some reactant X is going to be following a first order reaction, where the initial concentration, again, that's what this little knot here represents. This is our initial concentration, is 1.5 times 10 to the negative 6 molar. And we are also told that our rate constant, our K, is equal to 7.22 times 10 to the negative 3 inverse seconds. So our question is, what is the concentration of X at time equal to 100, as well as what is the reaction rate at our time equal to 100? So I'm going to give you guys the chance to just digest what we've been talking about so far, use the equations that we have learned to find our concentration X, as well as the reaction rate. All right, well, since we know, as we're coming together, that our reaction is a first order reaction, this tells us a lot about how this reaction progresses. This gives us information on the rate of consumption, this gives us information on our rate law expression, and it tells us which of the integrated rate laws we're going to need if we're going to be incorporating time into our calculations. So since the first thing we are asked to look for is the concentration of X at time equal to 100 seconds, let's just whip out the equation that we just learned. The natural log of our concentration of X is going to be equal to the negative rate constant times T added to the natural log of the initial concentration of X. So we are told what our rate constant is, we know what time we're at, and we know the initial concentration of our species, our reactant X. So we can just plug each of these variables in here. So we're going to be taking the negative rate constant, or negative 7.22 times 10 to the negative 3 inverse seconds. We're going to be multiplying it by our time, 100 seconds, and here we can see that our units are aligning. There's no conversion we need to do. So be paying attention to time units now, along with every other unit that we need to be paying attention to. But we can see that inverse seconds and seconds will be canceling out here, so we don't need to worry about any second units remaining in our final calculation of the concentration. So we're going to be adding to this the natural log of our initial concentration, which is 1.50 times 10 to the negative 6 molar. And here now we can see the molar unit is going to be remaining at the end. This is the only unit here that's not canceling out. All right, so let's solve for what's present on the right-hand side of the equation. So if we crunch our numbers appropriately, what we end up finding is that our value on the right-hand side is a negative 14.13. And I'm going to put a pin in the molarity unit just because natural log of molarity is kind of a strange thing to see, but that is what our unit is right now, is the natural log of molarity. So I'm just going to kind of leave that sitting up there for a moment and we can kind of ponder this answer. So what we have right now is the natural log of x is equal to negative 14.13. And it's very tempting if you're just, again, mindlessly crunching numbers to say, okay, well, my final concentration is negative 14.13. But that doesn't make any sense. You can't have negative concentrations. So what we have to recognize is that the left-hand side of this equation is natural log of x, and if we're asked to find the concentration of x explicitly, we're going to have to take both sides of this equation and raise it up into the exponent of e. This is going to pull down our concentration of x, canceling out e and the natural log on the left-hand side, giving us then a final concentration of e to the negative 14.13, also equal to 7.29 times 10 to the negative 7, and here we're just going to return the molarity to us. So since we had natural log of molarity and the exponent here, we also raised that up to the e, dropping down the molarity for our concentration unit. All right, so we can take a moment to analyze whether or not this answer makes sense. The way that we do so is to compare our final concentration to the initial concentration, which we could see again right here inside of our parentheses, initial concentration. As a reaction progresses, the concentration of our reactant should decrease. So your final concentration of reactant should always be less than the initial concentration you started with. So we can see that since our final concentration is something times 10 to the negative 7, our initial concentration is something times 10 to the negative 6, our final concentration does actually make sense here. All right, so we found what our x is equal to, and now we're asked to find the reaction rate, so we can also determine the speed with which the reaction is still progressing, since we can see that there's still reactant left over at this point, the reaction's not finished. Well, our integrated rate law doesn't actually explicitly have rate anywhere inside of it. However, this reaction is again related to the rate law expression. Since we're working with the same reaction here and the same conditions, our integrated rate law was in part found by using the equation of, or the rate law expression of rate is equal to K times the concentration of our reactant to the first power, since this is a first order reaction. So since we know now the concentration of our X, we can plug this into our equation here, and we also know our rate constant K since this was given to us. This means that now we can use our rate law expression to find not only the rate initially as the reaction begins, but the rate anywhere at any point in time, so long as we have used our first order integrated rate law. So our rate is going to be equal to our K, 7.22 times 10 to the negative third inverse seconds. And this is going to be multiplied by the X that we just found, which now I'm running out of space. So I'm going to, again, just draw an arrow like so. Our concentration of 7.29 times 10 to the negative 7th molar is what's going to be inserted right here. So the rate that we end up finding by taking these two values and multiplying them together is 5.26 times 10 to the negative 9, and our units here are molarity per second, since this is an inverse second, which is also a set of units that corresponds to a rate. So we can see that our units here are working out, and our answer overall, not negative 19, negative 9, excuse me. We can see that our rate here also makes some sense. It's a relatively small rate. It's a very small number, which means that we are not looking at a large initial rate. We are definitely looking at a rate that is further down the line as the relationship of our concentration to time is curved. We can assume that we're going to be somewhere out here where that slope is going to be a smaller value. So again, to kind of wrap up at this point, we have our first order integrated rate law, which is super useful for being able to linearly represent the relationship between concentration and time, assuming that our reaction again is first order. However, not every reaction is a first order reaction. So let's say hypothetically now we are looking at a reaction that is second order in its reactants. Explicitly, the following reaction is found to be second order in our reactant, chlorine monoxide. So we can see that 2 of our chlorine monoxides here are decomposing down into chlorine gas and oxygen gas. And the concentration of our ClO versus time we can see here on the right. So this relationship is not just curved, it is a much steeper curve initially, and it flattens out to a much more extreme degree as time progresses. And this is explicitly because the reaction rate is not just linearly dependent or like proportionally dependent on our concentration, but it is now dependent to a power of 2. So our reaction rate in terms of the rate law expression is going to be equal to our rate constant K times the concentration of chlorine monoxide squared. So we have our rate law expression here representing the rate as chlorine decomposes, and we also again have our rate of consumption equation, which explicitly incorporates a change in time. Now, just like the process with which we solved for the first order integrated rate law, we're going to here set these 2 right-hand sides, right, the middle and the right of our equation equal to each other. So the rate of consumption and the rate law expression, we are going to set equal to each other. And the goal in rearranging these equations, what we're solving for again, is the dependence of concentration on just a straightforward time variable. So again, we want to remove the change in time aspect. We're going to have to take an integral to do so. But the steps of performing that integral are the exact same as the previous steps. So if you would like to try that yourself just for some extra calculus practice, feel free to do so. If you're like, heck no, I don't want to do calculus, then you don't need to do so. But in following those same previous steps, what we derive is the second order integrated rate law. Now we can see the equation here looks differently than the first order integrated rate law, and that's because we have to do a different integral, like there's a different integrated solution when we follow the same types of steps as the derivation of our previous equation. So the second order integrated rate law is the rate law when observing that a reaction is second order in your reactant X. And at some time point, 1 over the concentration of X is equal to the rate constant K times T plus 1 over our initial concentration. So if, let's say, hypothetically, you're monitoring concentration versus time and you find that the relationship here is a curve, but you want to know what the explicit relationship is, the linear relationship between concentration and time, by taking the inverse of each of your concentrations and plotting them versus time, if your reaction is second order, you will find a straight line here, where the y-intercept, our b, in this y is equal to mx plus b equation, is equal to 1 over your initial concentration. The slope that we can see here is going to be straightforwardly equal to k. It is not equal to negative k this time, meaning that if, again, your reaction is second order and you take the inverse of your concentrations, you will get a linear relationship here, a positive slope. So your slope is equal to k. And if you want to know the concentration of your reactant at any point in time, we can use this second order integrated rate law to find what that concentration is. So we can use this equation in the exact same way as the first order integrated rate law equation that we already have seen an example of. If you know your K and if you know your initial concentration, you can solve for your final concentration at any time point t. And similarly, once you find your X, you can reinsert this back into your rate law expression. Rate is going to be equal to K times X squared to find your rate, also at any time point t as the reaction progresses. there is one additional order with which we need to talk about. So first and second order equations or reactions are the most common, at least at the general chemistry level. You learn more nuanced kinetics in the future. But there is one additional order that we have to talk about that is somewhat uncommon, but is still common enough that like we should address it now. So we're going to look at the time dependence of zeroth order reactions. A zeroth order reaction is one in which the rate does not depend on reactant concentration. In other words, your reaction rate will progress at the same steady pace because it is only temperature dependent, or if there are multiple reactants, it might only be dependent on the concentration of one and not the other. Now this is the case for what we see in the following reaction that we are told here is zeroth order in carbon monoxide. Now what this means is that we can see that we have two reactants and the rate is only going to depend on the concentration of NO. The rate does not depend on concentration of carbon monoxide. So what we would monitor as a function of time as this reaction progresses is that the concentration of our carbon monoxide would linearly decrease over time. The reason why there is this linear decrease is because the rate, again, is constant. There is nothing impacting the rate when it comes to carbon monoxide. So this looks a little strange. It's a little strange to think about because the reaction still moves forward. It's just not dependent on the concentration of one or possibly many of your reactants. So in order to approach rearranging and solving for the relationship between concentration and time, our math actually works out a little bit more simply. The derivative is a little bit easier because the rate, as we can see here, explicitly written, is dependent on concentration of CO to the zero. And since we know that like any number raised to the zero is just equal to 1, it turns out that the rate is constant, only dependent on the variable of temperature, or in this case, it would be dependent on a different reactant. But if we're not paying attention to that reactant and we want to be able to derive what's the concentration of our carbon monoxide as a function of time, we can go through the same steps as previously. Again, the integration actually ends up being much more simple. And our equation that we derive is known as the zeroth order integrated rate law. And the reason why it's so much easier is it turns out that the concentration of X already behaves linearly or changes linearly with time, so all we really need to look at is our rate constant as well as the initial concentration, and we don't need to like manipulate our concentration data at all. So we don't need to take any natural logs, we don't need to take any inverses. The integrated rate law, when observing that a reaction is zeroth order in reactant X, is just a straightforward linear relationship from the get-go. So this is confirmed again by turning our attention of concentration versus time data. We can see that this is already just a linear relationship. And so there's no manipulation that we need to do. If we plot concentration versus time, our slope is going to be equal to the negative rate constant, since this is a constant change, a constant relationship, a linear relationship. And our y-intercept b, again, because we're looking at a y is equal to mx plus b equation here, our b is going to be straightforwardly just equal to the initial concentration of x. So zeroth order equations may be a little bit more rare, but if we're ever faced with them, finding the concentration of that reactant X at some time point in the future is actually really straightforward, because the rate from the perspective of that reactant is only really dependent on our rate constant K. So if we take concentration versus time measurements, plot concentration versus time, we see that there's a straight line like out of the gate. What this means is that we have found our rate constant K, And the rate of our reaction, again, is only going to be dependent on K. There's no other reactant here with which we need to multiply this against. Our rate from the perspective of carbon monoxide is just proportional to the rate constant. All right, so let's talk about comparing our concentration versus time data experimentally. So we've already learned how we can take initial concentrations. Concentrations along with initial rates to find our rate law expression. And in finding our rate law expression, we have also been able to find our K as well as the reaction orders. Well, let's say it's just due to the reaction that you're working with, or due to limited quantities of your reactants, you're not able to take we're not able to take multiple data points using initial concentrations and initial rates. So let's say this method is just completely unavailable to you. You can't use it to find your rate constant or your rate order. But you can monitor a single trial as a function of time. Let's say you do have enough reactant to do that and you have the means to measure concentration versus time. Well, all you need is your concentration versus time data in order to determine the order of your reaction from the perspective of reactant X. And if you can determine what the order of your reaction is, you can also find your K by using the integrated rate laws. So the integrated rate laws are like an alternate means of being able to determine your K and your reaction orders experimentally. How you do so is by plotting concentration versus time and looking at the shape of your graph. For instance, if we just have concentrations and plot them versus times, which we can see is what is being represented by our graph here on the left, concentration in molarity versus time, we can see that this line is not straight. Since this line is not straight, it means that we are not working with a zeroth order reaction. Logically speaking, if our concentration versus time data was a straight line from the gate, that would signify a zeroth order reaction. But since it's not a straight line, we are not working with a zeroth order reaction. So the logic here is sort of like an if and only if statement. Like if the line is straight, it is zeroth order, and if it's not straight, it can't be zeroth order. So what we're going to do is manipulate our concentration data by taking the natural log of those same concentrations. So we're taking our concentrations here, natural log of the concentrations, plotting them versus time in the second graph here. Now we can see that there is a linear relationship. Because this line is straight, this signifies that we are working with a first order reaction. Right? Again, if and only if statements here. If the line is not straight, it's not that order. If it is straight, it is that order. So because the straight line here corresponds to natural log of X versus time, going backwards to our first order integrated rate law here, cleaning up the slide, natural log of X versus time providing us with a straight line does signify a first order reaction. It has to. Based off of the way that our integrations worked out, we know that this is logically true. All right, so if we come back to our data here, now this linear line is going to correspond to the natural log of concentration X is equal to negative KT plus the natural log of our initial concentration X. And so our rate constant K here, our negative K is equal to negative 0.0032. In other words, our K is equal to 0.0032. Because this reaction is first order, we also know what the units of our K are going to be. K explicitly is 0.0032 inverse seconds, because this is what the unit on our rate constant K is for a first order reaction in order to make sure that all of the other units work out and make sense. In addition, we can see that our y-intercept here signifies the natural log of our initial concentration. So if we want to actually find the initial concentration explicitly, like let's say we didn't even know exactly what that value was equal to, initial concentration of X is going to be equal to base of E raised to the 3 times 10 to the negative 15 value that is present here. Now let's say, just for the sake of comparison, we really want to make sure that this reaction is first order. Like, even though we already found a straight line, just for, giggles, we rearranged or manipulated our initial data again, not to be natural log, but instead to be inverse. Well, if we take the inverse of our concentrations of X and plot them versus time, we can see again, we do not have a straight line. This again emphasizes the if and only if relationship between our concentration versus time data. Like, we can manipulate this data in any way we want, but the only way that we get a straight line corresponds to the conditions that our reaction is a first order reaction. So because the inverse of our concentration versus time does not give us a straight line, this also means that it is not second order. No, we already knew it couldn't be second order because it has to be first order, but it's just a nice additional confirmation here. Now, I'm sure it feels like it's been a long lecture so far. In fact, we might have already called lecture at this point, but there's one last topic pertaining to the time dependence of a reaction rate that we have to talk about, which is the definition of what is known as the half-life. Now, half-life is more than just a valve game. It is, physically speaking, the time required for your reactant concentration to drop to half of its original value. Now, the half-life of a reaction is going to be a very useful thing to monitor when a reaction takes a very long time. For instance, radioactive decay can take centuries, all depending on what material is, or what material is breaking down. So it's going to be really nice for us to monitor how long it takes for even that initial concentration to drop in half, or then in half again, etc. So visually, we can represent what the half-life looks like graphically speaking, in the illustration down below. So what we're monitoring on the y-axis is molecules of N2O. So our N2O is the reactant we can see in this reaction here, where 2 dinitrogen monoxides will break down into 2 nitrogen gas molecules and a single oxygen. Well, if we start with 16 molecules, and this is going to be our concentration measurement here, we can see that it takes, according to this graph, 1 second for these 16 molecules to break down into 8, where this first jump is our first half-life, right? Our quote-unquote concentration of 16 molecules dropped down to 8. We've cut that in half, and it took, now we can see the correlation on our x-axis, 1 second to move forward. So we're going to label T1/2 as our half-life. This is equal to 1 seconds. Well, having determined this, we can now also predict, even if we didn't have the rest of this graph, that an additional half-life would take an extra second. In other words, at 1 second, or at an additional second, so 2 seconds total, we would expect the concentration of our molecules to drop in half again. And that is exactly what we see. It took 1 second for our concentration to drop from 16 to 8, another 1 second for our concentration to drop from 8 to 4. It's going to take an additional second for our concentration then to drop from, 4 to 2, which is not even labeled here on the graph. And it would take a 4th second, or an additional 1 second, for the concentration to drop, going all the way over here, from 2 to 1. So overall, we would predict that this reaction is going to take approximately 5 seconds for this reaction to complete. Now, graphically speaking, the limit here does not exist, but of course, physically, we know eventually we're actually going to run out of molecules. We're going to run out of things with which we can observe breaking down. And so somewhere between 4 and 5 seconds, we would expect this reaction to be done, as all of the reactant has been used up. So when a reaction takes an incredibly long period of time, Measuring our first half-life will give us an idea for what the rest of our graph is going to look like, and will also give us an approximate measure for how long it's going to take for our reactants to entirely break down. So the last thing that we really need to introduce today, the last new topic of conversation, are half-life equations corresponding to the rate order of your reactant. Because as we've already seen, the rate with which a reactant gets used up is dependent on its rate order, where a first order reactant gets steadily broken down as the rate progresses. A second order reactant, it has a power relationship with the rate and therefore it gets eaten up more quickly. 0th order reactants get eaten away steadily since they do not contribute themselves to the overall reaction rate. So how we can find the half-life, or the length of time with which it's going to take half of our initial concentration to be eaten away, can be found by inserting 1/2 of our initial concentration, literally in variable form, in for x in the integrated rate laws, and then rearranging and solving for t. So the integrated rate laws, again, as we have learned today, tell us the relationship between concentration and time. And so it's going to make the most sense to use these equations to determine what's the relationship between losing half of our concentration and time. So we're going to take half of our initial concentration of x, plug that in for our x in any one of our integrated rate laws, where each of the 3 that we've learned today can be seen in this table. And all we need to do then is rearrange and solve for t, since the initial concentration of x would hypothetically then either cancel out or make its way, like would remain somewhere in the equation as we rearrange and solve for t. So we can see the half-life expression, or the equation representing the amount of time that it takes, for initial concentration to be cut in half. Again, for a first order reaction, since that's what this first row here represents, is equal to 0.693 all divided by k. Now the 0.693 just comes about from how our math ends up working out as we rearrange and solve for our t 1/2. But what's really awesome about the first order rate law, like half-life expression, is that the half-life of a first order reaction is not dependent on your initial concentration of x. In other words, if your reaction is first order overall, the time with which it takes for half of your initial concentration to be eaten up doesn't depend on how much you initially had. The time progression is going to only depend on k. So you would expect your half-life the half-life time to increase, let's say as k decreases, or as like temperature decreases, if you could manipulate your like activation energy in some way. If k goes down, your half-life would go up, and vice versa. Like if you increase temperature, your half-life would go down instead, but there's no dependence on your initial concentration. So you could have 1 molar, you could have 2 molar, you could have 1/1,000,000th of a molar. The half-life is going to be the same. This will not be the case in our second order or our 0th order reactions, as we will see. So if your rate order in particular reactant X is second order, again, we're going to take this 1/2 of initial concentration of X, plug it in for X here, rearrange and solve for T. This will give us T of 1/2 is equal to 1 divided by our rate constant K times the initial concentration of X. So what this tells us is not only the half-life dependent on our rate order K, so it's, temperature dependent, activation energy dependent, etc. It's also dependent on the amount of initial starting material. So if you, let's say, had a greater concentration of X, you would expect your half-life to go down. In other words, the more reactant you have, the faster proportionally it's going to be eaten away. Last but not least, if we take this 1/2 of initial concentration X and plug it straight in for concentration of X in the 0th order integrated rate law equation, rearrange and solve for T, this is going to give us the half-life equation for a 0th order reaction, where there is also a dependence on the initial concentration of your reactant, but it's in a different place now. So what this represents is that our half-life is going to be inversely related to our rate constant K. This has been the same in all of our half-life expressions, but now we can see the initial concentration of our reactant is in the numerator. This means as we increase the initial concentration, our half-life is going to increase as well. This is because our rate does not depend on the initial concentration of X in a 0th order reaction. The rate is still plodding along at the same constant speed. So if you have more stuff in your reaction, it's going to take longer for it to react in a 0th order reaction. So how the half-life expressions again can be useful like in day-to-day life is if you're working with a very, very long time or a reaction that has a very, very long time span, and you can use these equations to predict their half-life. However, they can also be used in shorter reactions. There's no reason we can't use them, it's just they don't necessarily give us like the most useful information. All right, but let's get practice with these half-life equations regardless. So what is the half-life of a second order chlorine monoxide decomposition reaction where the initial concentration of your chlorine monoxide we can see was 1.5 times 10 to the negative 8 molar, and your rate constant is 7.22 times 10 to the 9, so 7 billion inverse molar times inverse seconds. Well, I don't think we have any time to waste here. It's been a very long lecture, so let's just wrap up this last example problem for the day. So we're working with a second order reaction, which tells us that if we are looking for a half-life, the equation that we need to use to solve for that half-life is equal to 1 divided by our rate constant K times the initial concentration of X, where X in this case is our chlorine monoxide. All right, so we are going to keep this 1 in the numerator. Obviously, it looks like we're working with an inverse here. Our K is going to go in for K, 7.22 times 10 to the 9 inverse seconds times inverse molarity times inverse second. And that's going to be multiplied by the initial concentration of our chlorine monoxide, 1.50 times 10 to the negative 8 molar. All right, so again, all of this is here in the denominator. It looks like molarity is going to cancel out. Since we are taking 1 over the inverse second, our half-life is going to be in the unit of seconds. So when we crunch the number, what we're going to find is that the time is 9.23 times 10 to the negative 3, and again, the time, or the time unit is going to be the second. So again, this decomposition reaction happens very quickly. From the get-go, it's going to take like 9,000ths of a second for half of our chlorine monoxide to just disappear. So this reaction progresses very quickly, and if we wanted to slow this reaction down, we could try to manipulate it with the temperature, so cool it down a little bit, or we could even have had less starting material. But ultimately, due to the incredible size of this rate law constant, our K, the reaction is going to progress relatively quickly, regardless of how we try to manipulate the speed of our reaction. All right, I think that was enough to talk about for today. So the dependence of your reaction rate and concentration on time is going to, as we saw, be a very complicated topic, but we can use these equations and a little bit of critical thinking to determine the variables that are being asked of us, whether it be a rate constant, whether it be a concentration, whether it be a time. We can use what we've learned today to solve for those variables. All right, so here we have a couple of section review problems. Again, please get as much practice as you can with this type of problem, since it does involve a little bit more critical thinking than the normal problem that we have worked with. You need to be able to analyze, think outside the box, evaluate which equation is going to be useful for you, all depending on what problem you're working with. So with practice comes comfort and ease and confidence, and that confidence here is going to be key. All right, well, if you have any questions, as always, please do not hesitate to let me know. If you have any homework, please do your homework. And until next time, class is dismissed.